Good morning, Pre-Calculus 30. We're about to start our next unit on exponential functions. If you haven't already done so, I would ask that you please complete the exploration activity in the student note packages on exponential function inquiry, decay, and growth. So please complete that. Once you're ready to go over the recap, then you can restart the recording. All right, so now that everybody's completed that, we can move on in our lesson here. So, first let's recap what you talked about. Which of the following functions are exponential? So I have y equals 2 to the x, y equals x squared, y equals 1 to the power of x, and y equals negative 0.5x. So if I graph these, I can see which ones are functions and which ones are not. But I don't necessarily need to do that. I can also look at our base and our power. So anything that has a base other than 1 raised to a power of unknown value, so x is an exponential function. So a would be an exponential function. B, however, would not be an exponential function because x is not in my exponent. So this would be called a quadratic function. C may look like it's an exponential function, but it's not because my base is 1. And we know that 1 to the power of anything is just 1. So that means that when I graph that function, I'm not going to get my exponential curve. I'm just going to get a line at y equals 1. This is not exponential. Also, in D, we would see that we do have a number raised to a power, but since this is a negative, this also isn't exponential. Because if I analyze it, negative 0.5 to the power of 1 would be negative 0.5. So when x is 1, I'd get negative 1/2. Then to the power of 2 would be 1/4. So it would come up here. And then to the power of 3, it would wind up a negative again. And then a positive when it's the power of 4, and then a negative. So this is just bouncing back and forth, which is not an exponential function. Remember, your exponential function can take on two forms, like that, a growth, or what's called a decay. Okay? So the next thing we're looking at is whether we see growth or decay in each of the following functions. So here we have y equals 2 to the power of x. Well, if you enter that into your calculator, graphing calculator, y equals 2 to the power of x, you will see it looks like this. This is a growth because as x gets bigger, right? As we move forward in x, y gets bigger. As we move to the right, we move up on our graph. Okay? Any number that is a whole number on the bottom, excluding 1, will be an exponential growth. Any number that is a fraction as a base will give us exponential decay. The reason this is called decay because as x increases, y decreases. As I move to the right on x, I wind up moving down on y. Notice you will never get a negative value on your basic exponential functions. You may when we start shifting them, but not today. So this is decay. Our first one was growth, by the way. Our next function, y equals 100x. Well, 100 is a whole number bigger than 1, so that means that this is growth. What's the difference between y equals 100 to the power of x and y equals 2 to the x? You can graph the two and see y equals 100 to the power of x is going to be much steeper because it is going to grow faster. Now we have y equals 0.8 to the x. Well, 0.8 is a number that is less than 1. We could think about it as a fraction. 8 over 10 to the power of x, which is 4 over 5 to the power of x. 4 over 5 is less than 1, so that means this will be decay. Be careful when you're looking at fractions because, for example, if I would have given you 5 over 4 to the x, this is bigger than 1, which means even though this is a fraction, this would be a growth. Okay. So let's talk about a few questions. Number 1, what is the y-intercept of any exponential function? Any exponential function goes through the same point as long as it's not shifted, and that is 0, 1. This happens because when we have any exponential function, let's say y equals 3 to the power of x, whenever x is 0, I'm going to get to the power of 0. Anything to the power of 0 is 1. Since all of our functions are going to have some base raised to the power of x, we're always going to get a y-intercept at 0 and 1. What is the x-intercept of any exponential function? Well, when you graphed it, you should notice our exponential functions do not touch the x-axis. This is because our x-axis is an asymptote. So we have a horizontal asymptote at y equals 0 because exponential functions never cross it. And our last one, what is the asymptote of any exponential function? Just like we talked about before, our asymptote is going to be y equals 0. The line y equals 0, because this is a vertical line on the x-axis. Sorry, a horizontal line on the x-axis. Okay. So our next page here. Graph the exponential function given by hand and identify the following: the x-intercept and y-intercept, whether the function is increasing or decreasing, the equation of the horizontal asymptote, the domain and range. We can actually do a few of these right now. I already know, just looking at our function, that this is going to be decay because it is a fraction, fractional base less than 1. I also know the horizontal asymptote is going to occur at y equals 0 because it's an exponential function and they always occur at y equals 0. And I already know there's going to be no x-intercept because it's not shifted at all. It's just a basic exponential graph. And our y-intercept is going to occur at 0, and that's a 1. Okay. Well, now, to look at domain and range, I could tell you what they are, but I want us to look at the graph before we go into it. So the first thing I'm going to put on is my horizontal asymptote along y equals 0, not forgetting that our asymptotes are always marked as dotted lines as they are not actually part of the graph. Now we're going to graph this. So to graph this, I can do one of two things. I can either memorize stretches and how this base changes things, or I can go to a table of values. We're going to go to a table of values. When you do a table of values, you want to have a few negatives, a few positives, and a 0 on there. So -2, -1, 0, 1, and 2. Remembering that we just take our x value and plug it in. So when x equals -2, I'll show you the work over here. 1/3 to the power of -2. Remembering that a negative in our exponent flips our base. So this is the same thing as saying 3 to the power of 2 or 9. When x is negative 1, this would be 1/3 to the negative 1. Negative simply flips our base, so we get a 3. When x is 0, anything to the power of 0 is 1. When x is 1, anything to the power of itself is 1/3. When x is 2, we wind up with 1 squared over 3 squared, or 1 over 9. Okay, so we can graph these. When x is negative 2, I'm at positive 9, so negative 2 and positive 9. When I'm at negative 1, I'm at positive 3. 1 and 0, of course. And then at 1, I'm at 1/3, so I'm going to cut this into thirds, 1/3. And then I'm at 1/9, so I'm almost touching it, but not quite. And so we could just draw our smooth, well, I can't draw a smooth one apparently, smooth exponential graph. Noting that it gets infinitesimally or extremely close to that asymptote, but never actually really touches it. Oops, sorry guys. All right, the last thing I need to look at are my domain and range. Well, we could see that our domain is actually all real values of x, because even though this graph is moving up slowly, eventually it could possibly touch all values of x. So our domain is x such that x can be any real number. Our range, however, we can see that y has to be bigger than 0. So y bigger than or equal, sorry, not equal. Erase equal. Y has to be larger than 0, and it can be anything in there. Okay, so that is our basic exponential function graph. All right, so now we're going to do our next step here, which is finding a graph, finding an equation given a graph. And we're given two exponential functions here. So the nice thing is that these are just going to be of some base to the power of x. So all we need to do is figure out what the base is. Don't need to worry about shifting, don't need to worry about stretching, just what that base is. So what we can do is actually look at each point and see what happens. So here, when x equals 1, y equals 4. That's really the only point that's going to help me. Because when x is negative 1, I'm wind up with some fraction, right? And here I've got all fractions, and I don't really have anything else that touches nicely. It looks like here when x is 1/2, it's about 2, but I'm not really sure of that. So I know that y equals 4 when my base equals 1. Y equals 4 when my base equals 1. The only thing that can make this true, c has to equal 4. So that means this graph is y equals 4 to the x. Okay, I'll ask that you try the next one, pause the recording, and try the next one before moving on. Okay, if we're ready, we're going to take a look at this. So I can see, again, this point 0 and 1 is there, but it's not really useful because it's on every other function, right? So let's take a look at the points I do know. I know that when x is negative 1, y is 2. And I know that when x is negative 2, y is 4. Just so we can have something a little bit different, we're going to work with this point. So I'm going to say y is 4 when x is negative 2. So when my base is negative 2. Okay? Well, that negative flips my base. So 4 equals 1 over c squared. So if I square root both sides, I'll get rid of the square on this side. So what we're going to do is square root both sides. So on the left here, I get 2 equals 1 over c. Now this is technically 2 over 1. So if I flip the right-hand side, I flip the next side. So I say c equals 1/2. Which means my equation is y equals 1/2 to the power of x. Okay? Now here, some people will be able to pick that up on a pattern, and that's fine. You could say, oh, well, 1/2 to the power of negative 1 gives me 2. 1/2 to the power of negative 2 gives me 4. And that's how you could pull it out. Or 1/2 to the power of 1 gives me 1/2. The only problem with that is you don't know that this is exactly 1/2. I mean, it looks like it, but you're not 100% sure. Okay, we've got a few more examples. Solving problems. So, applying exponential functions. Under ideal circumstances, a certain bacteria population triples every week. Write the exponential model that relates the number, or b, of bacteria to the time t in weeks, assuming the model starts with 1 bacterium. So if it triples every week, that means that every week I'm multiplying by 3. This is my base. So the total number of bacteria is 3 to the power of t. Because at 0 weeks, I have 1 bacterium. So that would be, at 0 weeks, I have 3 to the 0, or 1. At 1 week, I have 3 to the 1, or 3. At 2 weeks, I have 3 to the 2, or 9. Right? And you could go on with that. This is just to show you. This is your equation. Now, what are the domain and range of this function? Well, since it's an exponential function, exponential growth to be exact, I could say domain, x can be anything, because it's an exponential function that hasn't been shifted. Range, y has to be bigger than, don't do that again, Fritz. Bigger than 0. Because if I were to graph it, it would look something like this. My asymptote occurs on y equals 0. Okay, our last example. Determine approximately how many days it would take for the number of bacteria to increase to 8 times the quantity on day 1. So remembering, we have b equals 3 to the power of t. So they want to know, how long will it take this number to be 3 times the quantity on day 1? Well, on day 1, I don't want to go day 1. Quantity after week 1. Sorry, guys. Week 1, at the end of week 1, we have, so end of week, we have 3 to the 1, or 3 bacteria. Okay? Well, I want 3 times that. Sorry, I want 8 times that. So times that by 8, I want to know, when do we have 24 bacteria? Look at that, excellent English for you. When 24 bacteria. Okay. So in other words, I want 24 equals 3t. I want to know what t value is going to make this true. You can do it one of 2 ways. You can guess and check, keep putting numbers in for t until you get extremely close to 24. Unfortunately, that takes forever. The other, well, not necessarily forever, it's just going to take a long time. The other way we can do this is split it into two equations. Say y1 equals 24, y2 equals 3 to the power of t. Then graph it, find the intersection. I'm going to show you that on here. So my first equation is y equals 24. My second equation is y equals 3 to the power of x, or t. And I'm going to graph it. Can't see it, so zoom out. Zoom out. Oh, there it is. There's my intersection. Now on your calculator, you are going to have to press second function, calculate, then choose intersect, and go through the process we normally do. On here, I just have to click intersection, and it'll find me the intersection point. And once you do that, you should get 2.89 or 2.9 weeks. So t equals 2.9 weeks. They didn't ask us for weeks, though. They said how many days. Well, there's 7 days in a week, so I could just take that times 7 days per week, and I will get 20.3 days, or about 20 days, since I asked approximately. Okay. So that's your intro to exponential functions. If you have any questions, please feel free to email me. I should be able to get to them sometime shortly. So your homework for today, page 342 to 345. Two, 3, 2, 4, 5 BD, 8, 15, or 2, 3, 4, 5 AC, 7, and 10.